Hello students, this is Unit 3, Polynomial Functions. This is our test review. I'm not going to do all of the problems in the test review, but if you look down in the description, I'm going to try to drop a link of a public online calendar that I use, and you might be able to get to that and actually download the PDF of the test review, so you could follow along that way if you'd like. Okay, so let's get started. This is number 1A. Again, I'm doing select problems from each section, and we've been asked in number 1A to simplify the polynomial operation, rewrite it in standard form, and then name the polynomial. So this one is addition, so really we could ignore these parentheses and we could just look for like terms and combine like terms. So I have a 3x cubed and an x cubed, so I'll combine those first. And then I have a 2x squared here, but I don't have another x squared term, so I'm just going to add that in. And let's see, so I've done those two, and I've done that one. Now I have a -1 and a -9, so that's minus 10. It's already in standard form, and then I just need to name the polynomial. This is cubic. And remember, when it's in standard form, you're not going to add the exponents together. You're going to just go with the highest one and name it with that. So this is a cubic trinomial. It has 3 terms. Now the next one, this is 1C. I'm going to rewrite this without the parentheses, but I'm going to make sure that I basically distribute this negative or this minus into these parentheses, the second set of parentheses, because this is minus this whole thing. So every one of these things needs to be changed to its opposite. So I'm going to rewrite it. So everything in the first parentheses stays the same, and then the second one changes to the opposite. So you can see I've changed the 16x to the 6 to negative. This changes to negative, and this changes to positive. Now I just need to look for like terms. I have an x to the 6 term, and there's no other like terms there, so I'm going to just bring that down. And then I don't have anything else until my x cubed terms. I've got a -9, positive 8. That's negative x cubed. So I'm going to mark these out. Okay, and then I have a plus 6x squared. No like terms there. A minus 8x. And a minus 4. So I think I got everything. This is a 5 terms. 1, 2, 3, 4, 5 term polynomial. It is a 6th degree, so we're just going to call it a 6th degree. And I tell my students, if it's anything over 3 terms, just name it a polynomial. So it would be a 5-term polynomial, but you don't have to. I don't really make that distinction. I just call it a polynomial if it's over 3 terms. Okay, this is 1G, and this is multiplication. There's no plus or minus in between the parentheses, so this is 2 binomials multiplied times each other, so we're just going to distribute each one in. So we're going to distribute the 4xy squared first. 4xy squared times x is 4x squared y squared. 4xy squared times zy, and this is going to be plus 4xy cubed z. And then we will distribute this. X squared times x plus x cubed. X squared times zy is going to be x squared. We'll change that around to yz. Okay, so this is 4th degree, this is 5th degree, 3rd, and 4th. So we need this term right here to be first if we want to change it to standard form. And then the next one is going to be this one. And then after that one will be this one. And then the last one will be the x cubed. So that's standard form. This is 3, 4, 5, this degree, which we call quintic. And we'll just call it a polynomial. It's 4 terms. Okay, so we are moving on to the next section. Number 2 talks about end behavior, and we're looking at the a value and the degree to see if it's even or odd to determine the end behavior. So I want to look at the even degrees first. So I'm going to skip over this positive odd. If the a value is positive and the degree is even, then it's going to have arrows. And remember, end behavior just means we're looking at the arrows at the end. You could have all kinds of stuff going on in here. You could have all kinds of curves and bounces and all that, and passes and everything. But we're looking at the arrows at the end. So the end behavior, if you have a positive a value, which is the positive leading coefficient, and an even degree, the arrows are going to look like this. If you have a negative a value or leading coefficient and an even degree, the arrows are going to look like this on the left and right. So let's talk about end behavior and what this means. So on the left side of the graph, x is always approaching negative infinity. So you can always start out your end behavior like that. And then on the right side of the graph, x is always approaching positive infinity. So you could go ahead and write this on every end behavior, because that's always the case. Let me clarify. That is the case in polynomial functions. If we're talking about exponential functions, log functions, anything that has an asymptote, then we're not necessarily going to have x approaching negative infinity. There could be an asymptote where x could be approaching an actual value. But on these polynomial functions that we're looking at, you can start off every end behavior like this. So let's look at what our y's are doing. On a positive even, you've got both arrows pointing up. So obviously both y's are increasing or approaching positive infinity. So positive even, both of your y's approach positive infinity. And then negative even, both of them approach negative infinity, because both of those arrows are pointing down, which for our y's is a negative direction. All right, let's talk about odd degree. Odd degree polynomial functions, what I usually think about is if it's a positive a value, then as I trace from left to right, it ends up in a positive direction. So on the left side, it's doing this. And then on the right side, it's doing this. So no matter what's going on in here, as I trace from left to right, it ends up in that positive direction. Negative is the opposite. No matter what it's doing in the middle, it starts off that way, and then it ends up in a negative direction. Okay, so let's look at the, excuse me, the positive odd. The y's on the left side. So this is the left side of the graph. The y's are going in a decreasing direction or a negative direction. So y is approaching negative infinity. And on the right, y approaches positive infinity. Over here, it's the opposite. On the left side, y is increasing or approaching positive. And on the right side, oops, it's approaching negative. All right, so that's our chart. These, you might see these drawn, they might look like this on a chart, which is fine. I just draw them like this because there could be all kinds of stuff happening in the middle. We're just looking at the arrows for end behavior. End behavior means where does it end up? So this is number 2A, and the only thing we need to look at is this right here, this 5, and the fact that this 6 is a positive number. So this is a positive odd polynomial function. So remember, positive odd looks like that. So on the left side, it's approaching negative infinity. On the right side, y's are approaching positive infinity. So we would do the same thing we did on our chart. So this is the left side of the graph. This is the right side of the graph. And that's what it would look like. This is 2e. We're not actually given the function, but we're told the a value is positive and the degree is even. So if it's positive even, it's going like this. left side, positive infinity, right side, positive infinity. So this is what mine would look like. I put the word as in there because sometimes you'll see as. Sometimes you will see y called f of x or any other letter of x. You might see an a of x or a p of x or whatever. You might also see them the other way around. Like you might see y approaches positive infinity as x approaches negative infinity. So they could be the other way around too. Just be careful. I always look at the x and I look at the negative infinity because I know that's the left side of the graph. So that's what I look at first. So this is the left side, this is the right side. Okay, moving on to the next section. This is number 3A. And our instructions say, use the given information to state the x-intercept and what happens. In other words, does it bounce past our curve? So our x-intercepts are at 8, 0. Because remember, if you've got x minus 8, this is the factor, this is the root. So at 8, 0, whoops, there is an x-intercept. And what does it do at that x-intercept? My 2 tells me that it bounces. So we just usually put a little arrow and write bounce. And what that means is if this is your x-axis, then this is a positive. So it's going to come from here. Oops, let me go over here because that's at 8. So somewhere over here, it's going to come here, and at 8, it's going to bounce off, and it should be touching. It's going to bounce off that x-axis and go the other way. So that's what that would look like. At negative 2, 0, and then I've got a 3, 0. So these aren't in order, but at negative 2, 0, it would pass. And at 3, 0, it would pass. So negative 2, 0, it looks like it, this graph is not right. Let me see if I can draw a better picture of it. Okay, so I rewrote my intercepts in the correct order from the one to the very left to the one to the very right. So at negative 2, 0, first of all, this starts from an upward direction because it's a positive. Let's see, it's positive and it's even. So it's going to start from up here, and at negative 2, it's going to pass through the x-axis. And then at negative 3, it's going to come back through the x-axis like this. So this is a pass, this is a pass. And then at 8, it's going to come back down, and at 8, it's going to bounce off. So it's going to look something like that. Of course, you could always go over to Desmos and graph this and just make sure that this is kind of what it looks like, that it does pass at those two and bounce at the 8. Okay, this is 3D. Let's look at what we have here. We have a negative, leading coefficient, and we have 3 and 8, so that's an odd. I just want to kind of get an idea of what this would look like. All right, so x cubed. When you have an x like this by itself, this is the same thing as x plus 0 cubed. So this means there is a root at 0, 0. All right, so our first root is, we'll just put it here, is at 0, 0. And then our second root is at 6, 0. Now, I want to remind you that anytime you see an odd value, an odd exponent besides 1, this is a curve. And we'll talk about what that looks like in a second. And anytime you see an even value, any kind of even value is a bounce. Now, this one's going to look interesting because it's a little bit bigger even value than the 2. So it looks a little bit different. But what this one's going to look like, so at 0, it curves, and it's negative odd, so it's going to start from up here. It's going to start from up here. And then at 0, what it's going to do is it's going to look like this. So it kind of makes a little turn and then goes back the other way. And then at, excuse me, and then at 6, 0, it bounces. And that bounce is going to look a little bit wider than what you would normally see. So it's not just an immediate bounce off. It kind of goes to the x-axis and stays there for a second and then goes back the other direction. So this graph would look a little bit like this. So I went over to Desmos and I graphed this one. This is 3f. By the time you get to like a negative 7 cubed and a negative 9 to the 5th, the numbers are so large that you can't see like the bottom and the top of this graph. So I wanted to show you on Desmos what it looks like, but you can't see where the local minimum and local maximum are. So let's just talk about what it would look like. So I have x-intercepts at -5, 0, 7, 0, and 9, 0. Okay, let's talk about what it does. At -5, it passes. Anytime you have a 1 exponent, it's a pass. At 7, 0, it curves. And at 9, 0, it also curves, because anything above 1 that's odd is a curve. Okay, so let's see what this one would look like. This is a negative leading coefficient, and it is 5 plus 3 plus 1, so it is an odd degree. So negative odd means it's going to start up here somewhere. At -5, it's going to pass, so it's going to start somewhere up here, and it's going to pass through. Okay, and then it's going to come over here to 7, and it's going to make this curve, and it would look something like that. And then way up here somewhere, and this is like way down here, way up here somewhere, it's going to turn back the other way, and it's going to curve again at the 9, and look something like that. The only thing is this point was so far down here, and this point was so far up here, I couldn't see them on Desmos. Even zooming out, it made it so that you couldn't even look at the graph. But this is what it would do at each of these points. This curve will be, this one will be a little bit wider because it's a 5 instead of a 3. Okay, so this is number 4a, and it says write each polynomial in standard form. To be honest with you, unless it's complex roots, I don't see the point in writing these in standard form, so I usually tell my students keep it in intercept form. Every once in a while I'll say, nah, go ahead and do standard form just to get some practice multiplying everything out. But most of the time I just say just leave it in intercept form. So we're going to do intercept form right here. Let's look at our key things here in this. It says write a cubic polynomial. So cubic tells me something. That tells me it's going to have a total exponent of 3 when I add all the exponents. The roots, one of them passes at 1. So it passes at 1. And then it bounces at 4. And it also gives me another point that it goes through. If you are given another point like that, that means you need to find that a value. Okay, so let's see. Bounces at 4 would be a 2 exponent. This would be a 1 exponent. So this is how our equation would start out. We leave the a, and the y, and the x. But when we go to find the a value, we're going to use these two numbers right here. We're going to use this as the x value, and this is the y value. And we're going to just plug those in. So we're going to plug in an 8 for y. Leave the a unknown. We're going to plug in a 2 for both of the x's. And then we're just going to do the math to solve for a. So this is 1. Let's see, this is a times 1 times, that's -2 squared, 4. 8 equals 4a. So a equals 2 in this one. Now we just need to go back to our original equation and rewrite it with the 2 for the a. I'm going to leave this answer like this. Again, if it says standard form, what it wants you to do is it wants you to multiply all this out, write x minus 4 twice, and then multiply everything out. And I can give you what the answer would be, but I don't really worry about my students doing this. Here's standard form. Okay, speed this up a little bit. So this is standard form, this is intercept form, and either one of these is correct. Okay, this is 4C, and again, my instructions on the test review say write this in standard form, but we're going to leave it in intercept form. So it says write a quadratic polynomial. This means the total of the two exponents, or the exponents, is going to be 2, passes through both intercepts at 2 and -5. Okay, so that's how it starts out, and then we're going to use the 1 and the 30 to plug in for x and y to find the a value. So you need to plug in that x value everywhere you see the x. So a equals -5. We can just go back and rewrite our original, plugging in a -5 for a. that's it. We are still on section 4, and we've been given a graph and asked to write the polynomial function. So we need to look at this function and see what's going on here. Looks like we have 2 zeros, and the first one is right here. This is a really big curve, but we're going to use this right here as one of the zeros, and then there's another one right here. We also need another point on the graph that's pretty easy to see, and I always try to go for the y-intercept if I can. So we're going to say that this has a 0 at -6 and at 1. And then this other point that we're going to use is going to be 0, -4. It's always easier to use the y-intercept because your x ends up being 0. Okay, so we need to find the a value, but we first need to realize there's a curve at -6 and a pass at 1. So this is going to be x plus 6 cubed. And we use cubed, even though this could be a 5 or a 7 or whatever, but we use cubed because we really don't know with a graph which one it is. Okay, so that looks right. And then we're going to go back and plug in -4 for y, and then 0 for the x's. All right. So that's going to be 6 cubed, I believe. Let's see, let me make sure. 216. That's 216, and then that's -1. -4 equals -216a. Don't get confused. Don't divide by -4. We are dividing by coefficient of a. And I believe that's 1/54th. So let's see, I'll write it over here. A equals 1/54. So let's write our final answer down here. Again, it says write it in standard form, but we're going to leave it in intercept form because we can graph this on Desmos like this. There's no point unless you have complex roots. Okay, this is the last one we're going to do for number 4. We've been given another graph, and it looks like they've pointed out some points on this. We've got our zeros, and they've given us these 2 other points, but unfortunately they're not points that we can identify because they're between lines. But it looks like there's one right here that is on the graph that I can actually identify as, let's see, that would be 1, 3. So that's not too bad. We'll use that one as our point that's not a 0, so we can find the a value. So we have a 0 at 0, 1 at, what is that, 3. So we have 0, 3, and 7. And at all of them, it passes. And you can put an x minus 0 right here, or you can just put an x. It doesn't matter. Either way is fine. X minus 3 and x minus 7. Okay, and it passes at all of them. Okay, so let's plug in the 3 and the 1 to find the a. So I get 3 equals, that's going to be 12a. So divide by 12. A equals 1/4. Let me check and make sure. Yep. Okay, and then you know what? I'm going to change this to just 1/4 x because the x right here is also correct. All right, so that would be your answer, and if you wanted to write it in standard form, just multiply all that out. I'm not going to have you do that. Okay, so this is number 5a, and we're asked to graph and complete the table for each polynomial. So I usually just ask for a sketch on these, but I'm going to go over to Desmos and graph this one over there. If you're not one of my students and you haven't used Desmos, you just go to desmos.com. It's a free graphing calculator. You can actually just type in the function. If you're typing in like a y equals 25, you need to type in f of x equals 25. But if it's got the x's in the function, if it's not just a horizontal line, then you can just type it in. You don't have to put the f of x or the m of x. If you get in that habit, that's great, but you don't have to. So we're going to enter let's see, negative, and if you just enter / it will give you that fraction. If you hit the tab key, it'll bring you back up to the out of the denominator. Plus 5. Okay, so I've got my x plus 5, and that is squared. So you can use Shift 6 to bring it up to an exponent, and then hit tab again to bring it back down. And then x minus 3, and then that one is squared of 2. It's Shift 6 and then a 2. So this is what it looks like. And so when I do this for my students, I do this and I just take a screenshot. If you click on, you can click on the y-intercept, you can click on any minimums or maximums, local mins or local maxes. You can click on the zeros and it'll tell you what those points are. So I'm going to take a quick screenshot of this and come back. So this is my screenshot. If you were going to sketch this, you would mark the zeros and then that local minimum, the y-intercept, and then you could just sketch it real quickly. All right, so let's look at this. The a value, well, all they want to know here is it positive or negative? The a value is negative. The degree is 2 plus 2, which is 4, so the degree is even. You could also put quartic here. Either or both is correct. And behavior, well, on both sides of the graph, y is approaching negative infinity. So I'll do my left side and my right side. And then y approaches negative infinity on both sides. Zeros and multiplicities, it's got 2 zeros, and you just put in the ordered pair exactly as it's shown. We just usually draw a little arrow, and at both of these it bounces. And you would even know that without looking at the graph, because it's a 2 exponent. The x-intercept, I'm sorry, the y-intercept is at 0, negative 5. Local max, the 2 x-intercepts are local maxes, and that's just where it comes to a turning point at the top, and then it comes to a turning point at the bottom at the local min. Local minimum is this number right here. I usually tell my students you can round this to the 10th place. And then intervals of increase, let's point these out. Increase, negative infinity to negative 5, and then this is decrease, and then negative 1 to 3 is an increase. Decreases are here and here, and that's just like a roller coaster going up or downhill. Okay, so it's got 2 intervals of increase. Negative infinity to negative 5, and we've had an argument about whether to put brackets or parentheses here. My argument is it's neither increasing nor decreasing, but my key says give it a bracket, so I'll give it a bracket here. And then you use your symbol here, and then the other one is from negative 1 to 3. And again, I'm going to put brackets because that's what my key says to do. Okay, intervals of decrease, negative 5 to negative 1. And 3 to infinity. Whoops, not. Yeah, positive infinity because it's x values. Okay. Domain. The domain is all real numbers. It goes forever to the left and forever to the right. And the range, it starts at negative infinity. Always start at the bottom. Starts at negative infinity, and it goes up to y equals 0. So I feel like number 5 is really easy, and you can use this as a guide to do any of the other ones on number 5. So I'm going to skip over B and go to number 6. Number 6, complete the table. The given root is any of these up here. These are irrational and imaginary roots, complex roots. So if you have these, you're going to have that conjugate root with it. You're going to have the complex conjugate, which is its partner, so to speak. And so it wants to know what is the conjugate root. Okay, so for root 2, it would be negative root 2. For I, negative I. This would be positive root 5. So just change it to its opposite on all of these. This one's going to be negative cube root of 11. This one is kind of written backwards. Standard form for complex numbers is this. The complex conjugate would be minus 4i. So it's the imaginary part that gets changed to its opposite. And this one is in standard form. Complex conjugate would be 8 plus 9i. So this is where we actually have to start writing these in standard form because we don't want any i's in our final answer because we can't graph that. We can't graph an imaginary root. So when we write this, we're going to multiply it out and get standard form. Okay, cubic polynomial, zeros at negative 5 and I. Remember, if you have an I as a root, you are also going to have a negative I. They come in pairs always. So this one's going to look like this. Y equals, they gave us the A value, the leading coefficient. Excuse me, they have x plus 5 because it's at negative 5. And then x plus I, which is minus this number, because remember it's always x minus whatever the root is, and x minus I. So we need to multiply these things out to get standard form because we can't graph this. We cannot put this in Desmos or on our calculator. Okay, so I'm going to start with this set of binomials right here. I'm going to multiply those together and then multiply everything in next. I always multiply in my A value last. I'm just going to rewrite these. Okay, so x times x, x squared. Remember that when you have a plus and a minus and you have the same two terms, the middle term is always going to cancel out, but I'm going to go ahead and write it anyway just to show you. So this is going to be x times negative I minus ix, x times positive I plus ix, and then minus I squared. Okay, so let's figure out how to rewrite this. These two things cancel. This I squared is a negative 1, remember. So this is minus negative 1. Well, minus negative 1 is just plus 1. Okay, so now we have, bring these down again, and over here we have x squared plus 1. So now I'm going to multiply these two binomials together, and then lastly multiply in that negative 1/2. This is going to be x cubed plus 1x plus 5x plus 5. So it looks like I made an error here. It's not 5x, it is 5x squared. So no like terms. I need to multiply in my negative 1/2. So I'm going to do that next. Okay, so multiplying times negative 1/2 is the same thing as dividing by negative 2. So x cubed divided by negative 2, I'm going to write that. Well, you know what? I can just write negative 1/2 x cubed. Let's just do it that way. Okay? And then I'm going to do this one next because I'm going to try to get it in standard form. So 5x squared divided by negative 1/2, I'm going to write as minus 5 halves x squared. You could write minus 5x squared over 2. That's fine too. Okay, and then x times negative 1/2 is going to be minus 1/2 x. And then 5 times negative 1/2 is minus 5 halves. Okay, so just so you know, these two statements are equivalent to each other. They're the same thing. So it wouldn't have mattered if you wrote it out like this or like this. Either one of these would be correct. But we don't have any i's or any irrational numbers that we would have to try to graph in our answer in our standard form. Okay, so this one is a quartic polynomial, so I need it to add up to 4. It passes through the x-axis at all of these numbers. Now, it's quartic, first of all. Also, it has this irrational root, so it also has an irrational root of negative root 5. So what I have to do is I have to figure out what the a value is. But I'm going to have to change it to standard form before I can figure out the a value. So what I need to do first is write it with the a value unknown. So I'm going to put, I'm going to do x minus 0. I think it's easier to keep up with. X minus 1, x minus root 5, and x plus root 5. So I'm trying to find out what the a value is here. If I go ahead and multiply these complex conjugates together, then I can get something that's easier to work with than this irrational number. Okay, so let's do that part over here. This is going to be x squared. Now, negative root 5x and positive root 5x are going to cancel, so I don't need to put those. Minus root 5 times root 5 is 5. Anything, we've got the square root of something and we're squaring it, so that's going to give me x squared minus 5. So then I'm going to go back over here and rewrite this thing like this. Then I can find the a value. So now I'm going to plug in this for y and this for x. Okay, so I plugged those in. I did the math here. I got negative 3 equals negative 6a. So a equals 1/2. I can now go back and just plug in my a right here and then multiply this stuff out. I don't have to go back up here to this one because I had already multiplied those together. So y equals 1/2, and this is going to be just x here. I can put the x there now instead of the x minus 0. X minus 1, x squared minus 5. And then I can multiply these two binomials. And then I'm going to multiply this x in. And then I'll do the 1/2 last. So x to the 4th. I'm going to switch this around and make this standard form. Minus x cubed minus 5x squared plus 5x. Oops. Okay, now I can multiply in my 1/2. So I can do this as x to the 4th over 2. Or I can do 1/2 x to the 4th. That is my preferred way to do it. Oops, that should be a plus. Nope, that is a minus. I was thinking about the last problem. So minus 5/2 x squared plus 5/2 x. Now, if you're saying, why couldn't we just leave it like this? You can, because you can graph it at this point, but putting it in standard form is going to look like this. So I would probably accept either one of these on my test. Okay, this is 8b, and even though it doesn't look like it, this is a division symbol. We're told to use long division. We could use synthetic division with this because this is a linear divisor right here. But we're told to use long division, so we're going to do that. So I've gone ahead and set this up. We are missing the x squared term in the dividend. So I put in a 0 x squared as a placeholder. We're going to need that. Now what we need to figure out is we're using the x and the x cubed first. How many times is x divided into x cubed? Well, x cubed divided by x is x squared. And if you're not sure about that, put x cubed over x and then cross out or cancel out one of your factors from numerator and denominator, and you end up with 2x's, which is x squared. And then you need to multiply x squared times the divisor. And you don't have to write this down if you know what you're doing. X squared times x is x cubed. And x squared times negative 5x squared. If you don't get the same thing here that you've got here, you did something wrong. You need to go back and look at this again and divide it again. Next thing I want to do is change everything to the opposite of what it was, and then combine. So this and this, the x cubed and the negative x cubed, they cancel, and then 0x squared plus 5x squared is 5x squared. Bring down the minus 19x. 5x squared divided by x, and this is positive, is plus 5x. This times this is 5x squared. And 5x times negative 5 is negative 25x. Change these to the opposite. These cancel, and this is going to be positive 6x, bring down the negative 30. 6x divided by x is plus 6. This is 6x minus 30. Change to the opposite and combine, and these cancel and these also cancel, so we have a 0 remainder. So this is our answer up here. If we had a remainder, we would put plus or minus and then the remainder over the original divisor, but we don't. We don't have a remainder, so this is actually our answer here. Okay, so this is number 9A, and this one does instruct us to use synthetic division. You'll notice I put a 0 at the end because there was no constant term for this dividend, so I needed a 0 placeholder. So my coefficients were -1, 7, -9, -27, 54, and then my 0 constant. And then notice too that I put a positive 3 here because if this is the factor, we want to use the root here, so we want to change that to a positive 3. And then we bring down our first coefficient always, and then start multiplying and combining. Let's see, that is 40 plus 24. Oh, that's negative 54. Okay. 0, 0, 0. So I have no remainder, no constant still. This is my x term. X squared, x cubed, and x to the 4th. I started off with x to the 5th, so I should get an x to the 4th as my first term. So let's see, my answer is going to be negative x to the 4th plus 4x cubed plus 3x squared minus 18x, and that's it. So what this tells me is that 3 is a 0 for this function. Okay, so this is 9B, and we're told to use synthetic division. I want you to set this one up and then come back and see if you set it up correctly. So pause the video. I'm going to set mine up while I have it paused, and then come back. Okay, if you paused your video to set it up, you should have this. So we did not have an x cubed term. We also did not have an x squared term, so we would have put in 0 placeholders for those. Now, I would encourage you again to pause the video and then go ahead and solve this, or evaluate it, and then come back. So this is what it should look like after you worked it out. I'm going to move on, but you're welcome to pause your video again and get this work or see what you did wrong. So I believe we are on the last section, section 10, and this is 10A. We are asked to find all the zeros for the polynomial, so we need to factor this polynomial. I could do rational root theorem, but that's not something that we've really talked about. I gave my students a learning path on Khan Academy, so you might have done that. If you did, then you would figure out that there was a root that you needed to divide by. But I'm not going to do that here because I haven't talked about that with my classes. What I'm going to do is I'm going to say, okay, there are 4 terms here, so I think I can group these. I'm looking at this. I'm going to rewrite it so it's a little bit more spread out. Anytime you see 4 terms like this, first of all, look for a greatest common factor. I don't see one. So then after that, I'm going to divide this down the middle, and I'm going to take the greatest common factor of each side and then see if I can make it so that I can write this as 2 binomials. So let's do, this side is 3x squared is the GCF. And then once I take that GCF out, I have x plus 3 left. And then if I take the GCF out of this side, I take out 4, and that would be x plus 3 also. So now I have an x plus 3 that's a factor of each of these that I can take out. So one of my factors is x plus 3, and the other one is 3x squared plus 4. So I know that one of my roots then, if I set this up equal to 0, is going to be -3. So that's one of my answers. It looks like I need to have 3 roots, so I'm going to have 2 more that come from this. So we have 2 choices. We have to factor this right here. We could rewrite this as 3x squared plus 0x plus 4 and use quadratic formula. But what if we just set this up? I'm just going to try this. 3x squared plus 4 equals 0. So that would be 3x squared equals -4. And then if I divide by 3, I get x squared equals negative 4/3. So now the next step is going to be take square root of both sides. Now that means I have to take the square root of the numerator and the denominator. So I'm going to rewrite this up here because I think I'm going to run out of room. X equals square root of negative 4 over square root of 3. Okay, so I can make this a 2i. It's going to be plus or minus over root 3. Here's the problem. I can't leave this root 3 in my denominator. So what I have to do is what we call rationalize this root. Rationalize the denominator, sorry. So what I need to do is multiply numerator and denominator times root 3. And this is the same thing as multiplying times 1. So I'm not changing the value of this at all. When I do that, I get plus or minus 2i root 3 over 3, which is exactly the same thing I would have gotten with quadratic formula. I tend to not want to use quadratic formula if I don't have to. So the only thing that we haven't really discussed rationalizing the denominator here, but we can't have an irrational number such as root 3 in a denominator of a fraction. So what we have to do is multiply numerator and denominator times that, whatever that irrational number is. And that way it does what we call rationalizing the denominator. So we just multiplied it times 1. And our answer, so our 3 roots are negative 3, positive 2i root 3 over 3, and negative 2i root 3 over 3. And I didn't really talk about how I got the 2i over here, but this is square root of negative 1 times square root of 4. So that's going to be I, and that's going to be our plus or minus 2. I think we have a couple more we're going to do, and then we're done. So this looks like it's going to be about an hour video. Okay, so 10b is sum of 2 cubes. So we need to, first of all, use our formula that we learned to make this a binomial and a trinomial, and then we'll have to take that trinomial and use quadratic formula, I believe. Yes, we will. So if we use our formula that we learned, a equals x and b equals 3. So in our first set of parentheses, we have a plus b, which is x plus 3. And then the second set of parentheses, we square the a, and that's a minus there. And then we multiply the a times the b, and then we square the b. Okay, so one of our factors, one of our zeros is at negative 3. Okay, so that's one of them. Then we need to do quadratic formula over here. I'm going to pause it and set it up and go ahead and work it out, and then I'll come back to you. Okay, so what I did was I set up the quadratic formula. I'm going to finish it out and record it. So what I did was I highlighted, I don't want you to mix up the a and the b here with the a and the b here. This a, b, and c are for the quadratic formula to factor this trinomial here, because we have to do that to get our other 2 roots. I also highlighted where the a fits in, where the b fits in, and where the c fits into the formula. So let's finish this out. This is positive 3 plus or minus. This is going to be 9, negative 3 squared, and then minus 4. Oh, 4 times 1 times 9. I just need to do that. So 36. And then all of that is over 2. So 9 minus 36 is going to be negative 27. Write it down here. Negative 27, all that over 2. The square root of negative 27 equals square root of negative 1 times square root of 9 times square root 3. So this is going to be plus or minus, which we already have there, 3i root 3. So then let's see, y equals 3 plus or minus 3i root 3 over 2. So our other 2 factors are x equals, and we can separate these or you can leave them together. And just let me point out that these two are complex conjugates because we changed the plus to a minus. And remember, these conjugate roots always come in pairs. I'm going to try to fit in two more of these. Number 10C, we have a GCF that we can pull out first, and you always want to do that. We're going to pull out an x, and then we have x cubed plus 125. So this right here is sum of two cubes, where a equals x and b equals 5. So I can start off with a plus b, and then finish that out. That's going to be minus 5x plus 25. So I have two of my roots here. I need to have 4. X equals 0, because if I have an x right here, that's just a 0. And then x equals negative 5 from this one and this one. So I've got two of them. Now I need to use quadratic formula to solve this one. I'm going to go ahead and do all that and then come back to you. So before I show you quadratic formula for that one, let me go back to B and correct myself. I used a y over here, and I should have used x equals on all of these because those were the roots that we were trying to find. Okay, so I went ahead and did quadratic formula over here. I took a little shortcut here, but these are the two other factors using quadratic formula. And then these were the first two we found, so that's our 4 total that we know. So I wanted to show you kind of a little shortcut for finding a couple of the roots before we start to look for the irrational roots. I went to Desmos with, this is 10F, and I went to Desmos just to see if I could find any real roots, and of course there are 2 real roots shown here. So there is one at -1 and one at 2. So what I can do then is I can go over here and I can use synthetic division. I haven't been given those roots, but I can go to Desmos and find them. So I saw that there was one at -1. I don't want to put a comma there. There's one at -1, 0. Let's do it that way. And one at 2, 0. So what I can do is use synthetic division and divide both of these into what I get. And let me show you what I'm talking about. So I'm going to use synthetic division with the -1. I have 4, 3, 2, 1 constant. So I'm just going to use my coefficients. 1, -1, 14, -16, -32. I should get a 0 remainder. Let's see what happens. Yep. Okay, so I get a 0 remainder. And what I'm left with, this is my remainder constant, x squared, x cubed. So I have x cubed minus 2x squared plus 16x minus 32. Now what I can do is I can take my other root and divide it into this one. I already know 2 of the roots. So when I find the next polynomial after I use synthetic division again, then I can factor that. So I erased some stuff to give myself a little bit of room. Erase that. And I'm going to now use synthetic division with that the polynomial that I had gotten, the x cubed minus 2x squared and so on. And I'm going to divide that one by 2. Now why am I using a 2 here instead of a -2? Because this is not x plus 2. This is x minus 2. And if I was given the factor of x minus 2, I would use a positive 2 here. But I wasn't given a factor. I was given an actual 0. So I want to use my 2. And let's see what we get. We should get a 0 remainder again. Yep, we get a 0 remainder again. And so my last, this is remainder constant x squared. So I get x squared plus 16. I don't have to put that 0 there. X squared plus 16 is my last factor. So it was x plus 1 and x minus 2. So if I were to multiply all this out together, I would get this. So I hope this is making sense. Okay, so I cleaned up my space a little bit. So x minus 2 is this root, x plus 1 is this root, and then I've got this other thing here that I need to factor. I can use quadratic formula, but like I said, anytime I can avoid using quadratic formula, I just do. So I'm going to set this up Since I don't have a middle term, I can set this up x squared plus 16 equals 0. I need to take the square root of both sides. This is, so this is going to be plus or minus square root of negative 16. I just want to slow it down a little bit. Square root of negative 16 equals square root of negative 1 times square root of 16. So that is plus or minus 4i. All right, so my 4 roots, which I know because I have a 4 here that I have to have 4 roots. I just went over to Desmos and found the 2 rational ones so that I could use those, and I divided by those. I divided by negative 1 and then I divided by 2. And then I found my 2 irrational roots, or my 2 imaginary roots. So one of them is x equals 2, x equals negative 1, x equals 4i, and x equals negative 4i. You could have taken this and written it x squared plus 0x plus 16, and you could have used quadratic formula. I like doing this better because I think it's easier. And I think that'll do it. That is the last one I'm going to do from the test review. I hope this helped. Let me know if you have questions.